Wrap both your hands around something warm for a moment. A mug of tea on the table beside you, or just your own two palms pressed together under the blanket. Feel the warmth begin to cross over, out of the mug and into your skin, or out of one hand and into the other. Something is moving from the warm side to the cool side. It always moves that way, and it never, on its own, moves back. You have felt this every single day of your life, in every warm bath and every cold morning, and you have never once had to think about it. But here is the quiet, strange thing. The thing that kept careful people puzzled for the better part of 200 years. We can measure that warmth with almost absurd precision. We can say exactly how much of it flows, and how fast, and where it will settle. And for most of human history, nobody could tell you what the warmth actually was. What is the thing that crosses from the mug into your hand? What, when you say something is hot, is truly moving? Tonight, we are going to follow that question very slowly. From an imaginary fluid that everyone once believed in, all the way down to the trembling of single atoms and the smallest possible trickle of warmth the universe will allow. You do not have to stay awake for the end. You are welcome to drift off whenever you like. The warmth will keep crossing gently into you either way. Let's begin. Chapter 1. Start with the plainest fact there is. Some things are warm and some things are cool, and when you put them together, the warmth spreads out until they match. You know this in your body long before you know it in words. A warm stone held in a cold hand, the side of a mug that is too hot to hold, and then, a few minutes later, just right, a cold spoon dropped into hot soup, coming out warm. Bath water that starts almost too hot and slowly becomes ordinary while you lie in it. In every one of these, the same quiet thing happens. Warmth leaves the hot thing and gathers into the cool one, and it keeps doing that, patiently, until there is no difference left to even out. This is one of the first pieces of the world you ever learned. A small child reaches for a warm cup and pulls back, and reaches for it again, more carefully a little later, and in that reaching is a whole law of nature, learned by the hand before the mind has any words for it. Warm things cool, cool things, next to warm things get warmer. It happens so reliably, so gently, that you stop seeing it, the way you stop hearing the hum of a house you have lived in for years. And because it is everywhere, we gave it an easy name. We call it heat. We say the mug is hot, the night is cold, the oven is warming up. We talk about heat as if we know exactly what it is, the way we talk about water or air. It feels like the most ordinary substance in the world, something you could almost pour from one place to another. But stop for a second on that feeling, the sense that heat is a kind of stuff. When the warmth leaves your mug and enters your hand, what exactly has moved across? You can weigh the mug before and after, and it weighs the same. Nothing you can see has crossed over. No liquid, no smoke, no visible thread between the warm thing and the cool one. And yet, something has plainly traveled, because your hand is warmer now, and the mug is cooler, and that change is as real as anything you know. That is the question this whole night is built around. Not how hot, not how cold, not how to measure it, all of which we became very good at long ago. The deeper question, what is heat made of? When a thing is warm, what is actually different inside it compared to when it is cold, and when the warmth flows from the fire into the room, and from the room into you, what is the thing that is flowing? It is worth pausing to notice how honestly hard this question is, because the answer took some of the best minds who ever lived, and it took them a very long time, and they were wrong in interesting ways for most of it. For a long while, the most natural guess, the one that seemed obvious, was that heat really is a kind of fluid, an invisible, weightless something that lived inside hot objects and could pour out of them into cold ones. We will meet that idea properly in a little while and treat it kindly, because it was cleverer than it sounds. But hold for now just the shape of the mystery, the same way you might hold a smooth stone in the dark without looking at it. Heat is the most familiar sensation you have. It is the difference between comfort and cold, between raw and cooked, between alive and not. You have known it in your skin since before you were born, warmed by a body that was warmer than the world outside. And for all that closeness, for all that daily intimacy, what heat is at the bottom is one of the questions that quietly rebuilt physics from the ground up. Here is a small first clue, one you can test yourself without moving from where you are lying. Rub your two hands together, briskly, just for a moment. Feel them grow warmer. You did not pour any heat into them. There was no flame, no hot object nearby. You simply moved them against each other, and warmth appeared where there had been none. Somewhere in that plain little act is the whole secret, though it would take the world a surprisingly long time to read it. Motion, somehow, becomes warmth. Rubbing makes heat. Keep that quietly in mind. The warmth that comes out of movement, because we are going to return to it again and again, and each time we will understand it a little more deeply, until, in the end, it turns out to be almost the entire answer. There is no hurry to get there tonight. This is a question that has been sitting open in one form or another for centuries, and it is in no rush at all. It will keep perfectly well while you rest. You can let your hands go still now. Let them settle wherever they are comfortable, and let the warmth you just made fade back into the sheets. You do not have to hold on to anything. You only have to follow along, gently, as far as feels easy. So let this be the small seed we plant on the first night of the journey. You touch something warm, and warmth flows into you, and you have felt it 10,000 times without a thought. And underneath that plainest of feelings lies a question that reshaped how we understand the whole physical world. What is the warmth? What is truly moving from the mug into your quiet hand? We will take it slowly, one careful step at a time. And the first step, oddly enough, is to meet a substance that does not exist. For a long time, people were certain that heat was a fluid you could almost catch in a jar. They had good reasons to think so. Tomorrow in our telling, we will see why they believed it, and why, for a while, believing it was not foolish at all. For now, let the warmth even itself out around you. Let the room and your body come slowly to the same gentle temperature, the way all warm and cool things eventually do. There is nothing to solve before sleep. There is only the soft fact that you are warm and held, and that the oldest question about that warmth is content to wait for you until morning. Chapter 2. So, let us meet the fluid that was never there, and let us meet it with respect, because it fooled some very careful people, and it fooled them for good reasons. Picture the world as it looked to a thoughtful person a little over 2 centuries ago. You light a fire, and warmth streams out of it into the room. You take a pot off that fire and set it on the table, and the warmth slowly leaks out of the pot and spreads into the air. You pour hot water into a cold basin, and the two settle to a single middling warmth. Everywhere you look, heat seems to flow, exactly the way a liquid flows, downhill from where there is a lot of it to where there is little, until the levels match. If heat flows like a fluid, the simplest idea in the world is that heat is a fluid. That was the guess, and it was a good one. People imagined an invisible, weightless substance that soaked into things and made them hot and drained out of them as they cooled. The more of this stuff an object held, the warmer it was. When a hot body touched a cold one, the fluid simply ran from the fuller into the emptier, the way water finds its level between two connected cups. The French chemist Antoine Lavoisier, one of the most careful measurers who ever lived, gave this fluid a formal name. He called it caloric. He placed it among the basic substances of nature, alongside the ordinary elements, an invisible material that flowed in and out of everything, carrying warmth with it. And for a while, that was simply what heat was understood to be. Caloric, a thing you could not see or weigh, but which behaved in every visible way, like a liquid made of pure warmth. Now here is the part worth slowing down for, because it is easy to laugh at an old idea, and much more useful to see why it lasted. Caloric was not a silly notion. It actually explained a great deal, and it explained it well. Think about what happens when warmth spreads from hot to cold and evens out. A fluid running from full to empty does exactly that on its own, and never runs back uphill by itself. Caloric explained why heat only ever flows one way. Think about how a metal bar warms along its length when you hold one end to a flame, the warmth creeping steadily from the hot end toward the cold. A fluid soaking along the bar would do just that. Think about how the air around a stove warms up as if something were pouring off the metal and filling the room. Caloric could carry the picture of all of it. It even seemed to explain the way things swell when heated. Push more of this fluid into a substance, the reasoning went, and the fluid needs room, so the substance expands. Metal bars grow a little longer in the heat. Air pushes outward when warmed. A believer in caloric could nod at every one of these and feel that the world made sense. And this is the honest heart of the matter, the thing worth carrying with you. A wrong idea in science is not usually a foolish one. It is often a genuinely good explanation that happens to be pointing at the wrong thing underneath. Caloric matched a whole shelf of everyday facts. If you had lived then and thought carefully, you might well have believed in it too. It took the shape of the evidence honestly. It simply had the nature of heat backward, and nothing available at the time could yet show that. There was one loose thread, though, hanging quietly off the edge of the whole beautiful picture, and it is the thread the next part of the story pulls. If heat is a fluid, a real substance, then Any given object can only hold so much of it. There is only so much caloric in a cannon, or a stone, or a cup of water. Draw it all out, and the object should run dry, the way a sponge runs dry when you have squeezed the last of the water from it. A fluid is a thing you can use up. That is what it means to be a substance at all. So here is the simple test the world was walking toward, though no one had quite framed it yet. Can you get heat out of something forever? Can you keep drawing warmth from an object without ever emptying it? Because if you can, if the warmth simply never runs out, no matter how long you keep taking it, then heat cannot be a fluid sitting in a reservoir. There would be no reservoir deep enough. Something else would have to be making the warmth fresh as fast as you carried it away. Nobody set out to break the caloric theory on purpose. The crack, when it came from an ordinary industrial task, from a man standing in a workshop, watching metal being cut, noticing something that did not fit, and having the honesty not to look away from it. We will come to him in a moment, and to the plain, stubborn observation that started the long unraveling. For tonight, though, there is something rather lovely in simply sitting with caloric a while, this ghost of a fluid that everyone once felt sure of. It is a reminder that the world is often not what it plainly seems, even to the most careful eyes, and that being wrong, in a thoughtful, testable way, is one of the most useful things a mind can do. You do not need to hold any of this tightly. Let the idea of the warm, invisible fluid drift through you and out again, the way warmth itself drifts out of a mug left on the table overnight. There is nothing here to memorize, nothing to get right before you sleep. The people in this story had centuries to work it out, and they still had it upside down for a long while, and the world turned on gently all the same. Let your breathing slow a little. Let the picture of caloric settle softly into the dark, a beautiful wrong answer, resting now, waiting for the quiet observation that will undo it. Warmth, it will turn out, is not a thing you store. It is something closer to a motion you make, but that is for a little further on. For now, simply rest, warm and whole, while the old idea keeps you gentle company into sleep. Chapter 3. The quiet observation came from a cannon factory, and from a man who had lived several lives already by the time he stood in it. His name was Benjamin Thompson. He was born in the American colonies, and over a restless career he crossed oceans, changed sides, served kings, and eventually earned a title in Europe, becoming the man history remembers as Count Rumford. Around the end of the 1700s, part of his work involved the boring of cannon, the making of the long barrels by grinding out the center of a solid block of metal with a hard rotating tool. If you have ever watched anything being drilled, you know the next part in your body already. The work gets hot. The metal grows warm, then hot, then almost too hot to touch. In a cannon factory, the heat was enormous. The barrels and the shavings came off so warm that Thompson took to cooling the whole thing with water, and the water, given long enough, would come to a boil. Boiling water from nothing but a turning drill. Now a believer in caloric had a ready explanation, and it is worth hearing it fairly. When you grind metal into shavings, the story went, you break it into small pieces, and small pieces cannot hold as much of the heat fluid as the solid block could. So the caloric they can no longer keep gets squeezed out, and that squeezed out fluid is the warmth you feel. On the surface, it holds together. The cutting releases the heat that the shavings can no longer store. But Thomson had the instinct of a real experimenter, which is to push on an explanation until it either holds or breaks. He noticed something the tidy story could not survive. The heat did not stop. As long as the drill kept turning, the warmth kept coming, hour after hour, with no sign of running down. And the amount of metal actually shaved off was tiny. A small heap of dull metal chips, and from them, if the caloric story were true, would have had to come enough heat to boil pots of water again and again and again. So he set up a deliberate version of it. He used a blunt tool, one that barely cut the metal at all, so that almost no shavings were produced, and he let it grind against the barrel for hours while horses turned the drill. Almost no metal was broken loose, and yet the heat poured out just as freely, on and on, enough to bring water to a boil for as long as the horses kept walking. The warmth showed no sign of ever stopping. Sit with what that means, because it is the moment the fluid begins to evaporate. If the heat never runs out, no matter how long you keep drawing it, then it cannot be a fixed store of fluid hidden in the metal. There is no reservoir that never empties. Something was making the heat fresh continuously for as long as the motion continued, and the one thing being supplied without pause, the one thing that never ran dry as long as the horses walked, was the movement itself, the turning, the grinding of surface against surface. Thomson drew the bold conclusion out loud. Whatever heat was, it could not be a material substance, because you could produce it without limit. It had to be something that motion could generate. He suspected, in plain words, that heat was a kind of motion, though he could not yet say the motion of what. Around the same time, on the other side of the story, the young English chemist Humphrey Davy is said to have pressed the point with an even simpler picture. Take 2 pieces of ice, colder than freezing, and rub them together. By the fluid theory, ice is already low on caloric, so there should be little to give. And yet, with nothing but the rubbing, the ice can be made to melt where the surfaces meet, and melting takes warmth. The friction itself was supplying it. However the details are told, the moral is the same one you found with your own hands in the dark a little while ago. Rubbing makes heat. Motion makes warmth. Apparently out of nowhere, for as long as you keep moving. This did not overturn the caloric theory overnight. Good ideas, even wrong ones, do not fall the moment they are pushed. Many careful people found ways to keep the old picture standing for years yet, patching it here and adjusting it there. And that too is part of how science honestly works. But the crucial thing had been seen and could not be unseen. Heat was not a fixed treasure locked inside matter. It was something you could pour out endlessly, as long as you kept doing work, as long as something kept moving. And notice how the mystery has quietly shifted its shape. We began with heat as a substance, a fluid you might store and spill. Now it is starting to look like a happening, an activity, something a thing does, rather than something a thing contains. The warmth in the cannon, was not being released. It was being made out of the plain mechanical effort of the drill. That leaves a beautiful open question hanging in the workshop air, the question the next part of our journey answers. If motion becomes heat, then exactly how much heat does a given amount of motion make? Is there a fixed rate of exchange? A steady price at which movement buys warmth? Because if there is, if so much effort always yields precisely so much heat, then heat and motion are not merely cousins. They are the same thing wearing two different faces, and you could prove it with a careful enough scale and a patient enough afternoon. There is no need to chase that tonight. Let the horses in the old story keep walking their slow circle, turning the drill, warming the water, while you lie still and let your thoughts slow to a stop. You have already felt the truth of it in your own hands. That is enough understanding for one night. Let your shoulders loosen and sink. Let the warmth of your body be, for now, simply a fact you rest inside, without needing to know yet what it is made of. The answer is coming, gently, a step at a time, and the next step is a man, a bucket of water, and a small falling weight measuring the exact price of warmth. That, though, can wait for you. For now there is only the quiet and the slow turning of the story, and sleep coming on as softly as heat leaving a cooling room. Chapter 4. The man with the bucket and the falling weight was an Englishman named James Prescott Joule, and he grew up in a brewery. That detail matters more than it seems. A brewery is a place obsessed with temperature, where a fraction of a degree can decide whether a batch is good or ruined, and where people measure warmth carefully for a living. Joule learned that habit of exact measurement early, and he brought it to a question that many thought was too vague to measure at all. He wanted to know the price of heat. Not to describe warmth in general terms, but to pin down in hard numbers exactly how much heat a given amount of motion would make. His most famous experiment is simple enough to picture as you lie there. Imagine a wooden bucket of water. Inside it, a set of paddles on a shaft, like a little water wheel turned on its side. Outside, a cord runs over a pulley to a weight. When the weight is let go, it falls, and as it falls, it turns the paddles, and the paddles churn the water. That is the whole of it. A falling weight, stirring water. Now the falling weight has a plain, measurable amount of energy of motion. Joule knew precisely how heavy it was and exactly how far it dropped. So he knew exactly how much work the fall represented, and the churning paddles, pushing against the water, warmed it very slightly by friction. The water fought the paddles. The paddles stirred the water, and the temperature crept up by the smallest amount. Joule had thermometers delicate enough to catch that tiny rise, fractions of a degree, and the patience to do the whole thing over and over until he trusted the result. What he found is one of the quiet cornerstones of all physics. Every time a given amount of falling motion produced the very same amount of warming, the exchange rate never varied. So much work by the weight, so much heat in the water, always in the same fixed proportion. Motion did not merely cause heat in some loose way. It converted into heat at a definite, repeatable rate, the way one currency changes into another at a fixed price. He had measured what came to be called the mechanical equivalent of heat, the exact toll at which movement becomes warmth. Let that land softly, because it is the moment two things that seemed utterly different are shown to be one. On one side, the plain mechanical world of falling weights and turning wheels, the world of pushes and motion. On the other, the warm world of hot water and thermometers, the world of heat. Joule threw a bridge across the gap and showed that the traffic between them runs at a fixed rate in both directions. Heat is not a separate substance that happens to be released by motion. Heat is a form of energy, the same energy that lived in the falling weight, simply arrived at a new address. This was the piece that let a larger, grander idea click into place. One of the deepest principles we have. Energy is never made from nothing and never quietly vanishes. It only changes form. The energy of the falling weight did not disappear when the weight came to rest at the bottom. It went into the water as warmth. The chemical energy in a lump of coal becomes the heat of a fire and the motion of a steam engine. The energy of your last meal becomes the warmth of your body and the movement of your hand as it rests on the blanket. Nothing is lost. It is all handed on from one form to the next in an unbroken accounting. Joule met resistance at first, and it is easy to understand why. His temperature changes were so small and his claims so large that many did not believe such delicate measurements could carry such heavy conclusions. It took time and the support of other careful thinkers before the world accepted what his patient afternoons had shown. That too is the ordinary rhythm of the thing, a quiet result, doubted, repeated, and slowly believed. But once it was believed, the shape of the mystery had changed for good. Heat was now firmly a form of energy, and energy could flow between motion and warmth at a fixed and knowable price. The old fluid, caloric, had no work left to do. There was nothing for it to explain that this new picture did not explain better and more simply. And yet notice the beautiful gap that remains, the gap that carries us into the very heart of the story. We now know that heat is energy and that motion turns into it at a definite rate. But we still have not said what is moving. When the warm water in Joule's bucket holds all that energy the weight gave it, where is the energy sitting? What, inside the water, is now carrying the warmth that the falling weight handed over? The paddles have stopped. The bucket is still. On the outside, nothing moves at all. So where did all that motion go? The answer is that the motion did not stop. It only became too small to see. It went down into the water itself, into pieces far below the reach of any eye, and there it is still going on, and it has never once paused since. That is where the next part of our journey takes us, down beneath the surface of still things, to discover that nothing warm is ever truly still. There is nothing you need to do with this yet. Let it rest at the edge of your mind, this idea that the stillness of a warm cup of water is only the stillness of the outside, and that underneath something is moving that will not stop. Let your own body grow heavy and quiet now. The energy of your day is settling, handed gently on into warmth, the way it always is. You do not have to follow the weight any further down tonight. Let it fall slowly through the dark on its cord, turning the paddles, warming the water by the smallest breath of a degree, while you let go and grow warm and drift toward sleep. Chapter 5. So let us go down beneath the still surface of a warm and quiet thing and find out what is moving there. The idea, when it finally arrived in full, is so simple that it can be said in a single breath. Everything is made of tiny pieces, atoms, and the little clusters of atoms we call molecules, and those pieces are never still. In a warm thing they move quickly. In a cool thing they move slowly. Heat is that motion. Warmth is the trembling of the small parts of matter, and temperature is a measure of how briskly they tremble. That is the answer the whole first half of our journey has been walking toward. Heat is motion, the motion of the pieces too small to see. The first serious version of this thought came surprisingly early from a Swiss thinker named Daniel Bernoulli, well before the fluid theory had fallen. He imagined a gas, the air in a room or in a sealed vessel, as an enormous swarm of tiny particles flying about in every direction, bouncing off the walls and off each other. The pressure the gas pushes against its container with, he suggested, is simply the drumming of countless little impacts, all those particles striking the walls, moment after moment, and if you heat the gas, the particles fly faster and strike harder and push out more strongly. It was a lovely, clear picture, and it was mostly ignored for the better part of 100 years, because caloric was in fashion and the world was not ready. When the picture came back, it came back with real force, carried by a handful of remarkable minds. The German physicist Rudolf Clausius laid down its careful foundations, taking seriously the idea that heat simply is the motion of molecules and working out what must follow. The Scottish physicist James Clerk Maxwell did something even more daring. He accepted that in any warm gas there are so many particles moving so wildly that no one could ever track a single one, and he asked a cleverer question. Not how fast is any one particle moving, but how are all their speeds spread out? How many are moving slowly? How many quickly? How many somewhere in between? That shift is worth pausing on, because it is a genuinely different way of thinking, and it is the birth of a whole branch of physics. Maxwell stopped trying to follow the individuals and started describing the crowd. He found that in a gas at a given temperature, the speeds settle into a definite pattern, a smooth spread. Most particles cluster around a typical middling speed, with fewer very slow ones and fewer very fast ones tailing off at the edges. Warm the gas, and the whole spread shifts toward higher speeds. The temperature you feel is really a statement about that crowd, about the average energy of motion of an unimaginable number of tiny things. Then came the Austrian physicist Ludwig Boltzmann, who took this statistical way of seeing and pushed it as far as it would go, tying the motion of molecules to the large, warm behavior of everything we can touch. Between them, these thinkers built what we call the kinetic theory of heat, the understanding of warmth as motion. And it works. It explains why a gas pushes harder when heated, why it expands, why pressure and temperature and volume dance together the way they do, all of it flowing from the single picture of tiny particles in ceaseless flight. Now bring that picture home to where you are lying. The air in your room, which feels so calm and empty, is in fact a storm of countless molecules, flying in every direction, colliding billions upon billions of times each second, striking your face and your blanket and the walls in a steady invisible rain. It feels like nothing, like stillness, only because there are so many of them, and each is so small that all you sense is a smooth, gentle pressure and a mild warmth. The calm of the air is the calm of an enormous crowd, not the calm of an empty room, and the same is true of solid things in their own way. The wood of the table, the ceramic of the mug, the frame of your bed. The atoms in a solid are not flying freely. They are held in place, bound to their neighbors. But they are not still. They quiver, they jitter, each one trembling around its fixed spot, jostling the ones beside it, a whole locked lattice shivering in place. Warm the solid, and the shivering grows wider and wilder. Cool it, and the trembling calms toward a whisper. When you touch something warm, the fast trembling of its atoms nudges the atoms of your skin into trembling faster too. And that spreading of the tremble from their pieces into yours is the very warmth you feel crossing over. This is the answer to the question we set out with, or at least the deep classical half of it, when warmth flowed from the mug into your hand. On the first night, no fluid crossed the gap. What crossed was motion. The briskly trembling atoms at the surface of the mug jostled the slower atoms of your skin and set them moving faster, handing the trembling along, particle to particle, the way a nudge passes down a line of people standing close together. Heat is not a thing that travels. It is a motion that spreads. Feel for a moment how strange and lovely that makes the world you are resting in. There is no such thing anywhere as a warm object at rest. The stillest, quietest, most solid thing in your room, the wall, the floor, the book left open on the chair, is on the inside, a shimmering blur of trembling atoms, never pausing, never once falling still, as long as it holds any warmth at all. Your own body, warm under the covers, is a vast and gentle commotion of trembling pieces, and that commotion is exactly what it means to be alive and warm rather than cold. You do not have to picture all of it. Let the image be soft. Everything around you, faintly and endlessly trembling, and you among it, warm, because you tremble too. There is nothing to hold, nothing to keep track of. Just the quiet knowledge that stillness, at the smallest scale, does not exist, and that the warmth wrapped around you tonight is really the soft, ceaseless motion of the world. Let that trembling rock you gently, the way a crowd's murmur can become a kind of quiet. You are warm. That warmth is motion far too small to see, and it will go on all night on its own, asking nothing of you. Let your thoughts slow while it keeps moving, and let yourself sink toward sleep held inside the gentle shimmer of a world that never entirely stops. Chapter 6. There is a curious thing about that trembling, something you have known your whole life without ever putting it into words. The warmth always goes one way. Think back to the very first thing we noticed together. Heat flows from the hot thing into the cool thing, never the other way round on its own. The warm mug heats your cold hand. Your cold hand never, by itself, makes the warm mug hotter still while your fingers turn to ice. The hot bath cools toward the temperature of the room. The room, a room on its own, never gathers its warmth back into the water and leaves the bath steaming while the air goes cold. This one-way flow is so familiar that it feels like nothing at all. But underneath it lies one of the deepest and strangest facts in all of physics. The physicist Rudolf Clausius, whom we met building the picture of heat as motion, was the one who gave this one-wayness a name and a precise shape. He noticed that in every real process involving heat, something always increases, some quantity that never runs backward. He called it entropy. In his careful hands, it was a bookkeeping quantity, a way of tracking how heat spreads and why it will not gather itself back up. Heat flows from hot to cold, entropy rises, and the world takes one more irreversible step in the only direction it ever takes them. But it was Ludwig Boltzmann who saw what entropy really is underneath, and his insight is one of the most beautiful in science. So let us take it slowly. Remember that a warm thing is a crowd of countless trembling particles. Now, there are a staggering number of different ways for those particles to share out their motion. The warmth could be spread evenly among them, or it could, in principle, be bunched up, with a few particles carrying almost all the motion and the rest nearly still. Both are possible arrangements of the same total energy. Here is the quiet key. There are almost unimaginably more ways for the motion to be spread out evenly than for it to be bunched up. Spread out, shared, evened off arrangements are common, countless, ordinary. Bunched up, lopsided, concentrated arrangements are rare, few, special, and a crowd of particles jostling and colliding at random, blindly, with no plan, simply stumbles into the common kind of arrangement, far more often than the rare kind, for the plainest reason there is. There are so many more of them to stumble into. That is why warmth spreads. That is why heat flows from hot to cold and evens out. Not because anything is pushing it, not because of any force with a direction, but because evenness is overwhelmingly more likely than concentration. When you are dealing with numbers this vast, a hot spot in a cold room is a rare, bunched up arrangement. Left alone, the endless random jostling shuffles it, inevitably, toward the far more common state where the warmth is shared out smoothly and no spot is hotter than another. Entropy is at bottom just this, a measure of how spread out, how shared, how ordinary an arrangement is, and it rises because the world, shuffling itself blindly, drifts always toward the more ordinary. Now here is the thought that has kept thinkers up at night, though tonight it can gently do the opposite for you. This spreading is the reason time has a direction at all. Almost every basic law of physics works exactly the same forwards and backwards. A film of 2 billiard balls colliding looks perfectly sensible played in reverse, but a film of a drop of ink spreading through a glass of water, or warmth leaking from a mug into a room, looks obviously wrong when it runs backward. We laugh at it because we have never once seen ink gather itself back into a drop, or a lukewarm room hand its warmth back to make the coffee hot again. The one-way spreading of heat, the steady rise of entropy, is the deepest reason we can tell the past from the future at all. The arrow of time is written in the way warmth spreads. Sit softly with that for a moment. because it is genuinely one of the grandest ideas humans have found, and it is hiding inside the plainest event in your kitchen. Every time a hot drink cools on the counter, the universe is quietly showing you why tomorrow is different from yesterday. The warmth spreading out, the motion sharing itself among more and more particles, evenness winning over concentration. Because there is simply so much more evenness to go around. That is the current the whole world drifts along, always in the one direction, from the special toward the ordinary, from the gathered toward the spread, and there is something oddly restful in it if you let there be. You do not have to hold your warmth together tonight. You do not have to keep anything gathered or concentrated or defended. The natural direction of things is to soften, to spread, to even out and let go. Your warmth will drift gently into the sheets and the air, and that drifting is not a loss, but simply the way the world moves. The same way it moves the ink through the water and the heat through the room. The same way it always has and always will. So let yourself follow that current instead of fighting it. Let the day's warmth and the day's tightness spread out and even off, sharing themselves into the quiet around you. There is nothing to keep hold of. The most natural thing in the universe is exactly what your body wants to do now, which is to loosen and settle and let the warmth find its level. We have found, then, that heat is motion and that its spreading gives time its direction. But there is a question we have carefully stepped around, and the next part of the journey walks straight into it. If warmth is motion, and cooling is that motion calming down, then what happens if you keep cooling? Could you slow the trembling all the way to nothing? Is there a coldest possible cold, a floor beneath which no thing can fall? And when we go looking for that floor, we find the ground of the whole classical story quietly giving way. For now, though, let the warmth spread, and let the day even out and rest. Chapter 7. So we go looking for the floor. If warmth is the trembling of tiny things, and cooling is that trembling slowing down, then somewhere, surely, there must be a coldest cold, a place where the motion runs all the way out. Follow the logic gently. Take any warm thing and cool it, and its atoms tremble a little less. Cool it further, and they tremble less still. Keep going in your imagination, taking away more and more of the motion, and the trembling grows fainter and fainter. It seems obvious where this must end. At some lowest temperature, the motion would reach zero. The atoms would come completely to rest. There would be no warmth left to remove, because there would be no motion left at all. That would be the true bottom, the coldest anything could possibly be. The Scottish physicist William Thomson, later honored with the title Lord Kelvin, worked out where that bottom must lie. By studying how gases shrink as they cool, he saw that they behaved as if, at one specific temperature, far below anything in ordinary life, all their motion and pressure would vanish together. He proposed a temperature scale that begins there, at that absolute bottom, rather than at the freezing point of water. On that scale, which we still use today, and which carries his adopted name, 0 means the true zero, the point where, in the classical picture, all trembling ceases. We call it absolute zero, and it sits far below the coldest winter night, far below the cold of deep space, a cold that nothing in the natural universe quite reaches on its own. Now, one thing about absolute zero is settled and certain, and it is worth saying clearly and calmly. You cannot actually get there. Not because our machines are not good enough yet, but as a matter of deep principle. Every method of cooling works by carrying warmth away from a thing into something colder, and as you approach the absolute bottom, each further step steals a little less and costs a great deal more. You can creep closer and closer to within a whisker of it, closer than you might believe possible, and laboratories have come astonishingly near. But the last tiny gap can never quite be closed. Absolute zero is a shore you can approach forever and never land upon. For tonight, that alone is a soft and reassuring thought. There is a gentlest possible quiet at the bottom of all things, and the universe leans toward it, cooling slowly over ages, but never slams the door shut, never reaches the dead stop. Even the coldest reaches of space still carry a faint whisper of warmth. Perfect. Total stillness is simply not on offer anywhere. But here is where the story we have been telling, the beautiful classical story of heat as ordinary motion, quietly runs into its own edge, because the classical picture makes a very clear promise about that bottom. It says that at absolute zero, the trembling would stop completely. Every atom frozen in place, zero motion, a perfect, absolute, final stillness. That is what the old picture demands. Take away all the heat, and you take away all the motion, right down to nothing. And that turns out not to be true. When physicists in the early 20th century looked closely at what happens to matter as it approaches absolute zero, the numbers refused to behave the way the classical story insisted they should. The trembling did not simply fade smoothly toward zero. Something odd happened down there in the deep cold, something the picture of ordinary jiggling particles could not explain. The way materials store and release warmth changed its character as they got very cold in ways that made no sense at all if heat were simply motion in the plane. Everyday meaning of the word, it was a small discrepancy, in a sense, a matter of careful measurements, not matching a confident theory in the coldest, most extreme conditions. But small discrepancies, honestly faced, are how the deepest revolutions begin. The trouble in the deep cold was one of several quiet cracks appearing at the edges of classical physics at the same time, all of them whispering the same unlikely thing, that down at the smallest scales, energy and motion do not behave the way they do in the ordinary world of buckets and paddle wheels. That warmth, when you follow it all the way down, is not quite the smooth, continuous, endlessly divisible thing it appears to be. We are standing, in other words, right at the doorway of the quantum. Everything so far, the fluid that failed, the endless heat of the drill, the price Joule measured, the trembling atoms, the spreading warmth, and the arrow of time, all of it belongs to the classical world, the world at the scale of things we can see and hold. It is beautiful true, and it is not the whole truth. To learn what heat is really made of, at the very bottom, we have to step through that doorway into a world where energy comes in pieces, where trembling never fully stops, where the smooth becomes grainy and the certain becomes strange. That step is the true turning of our whole night, and we will take it gently on the far side of a rest. There is no need to rush it across the threshold now. It has stood open for more than 100 years, and it will stand open a while, longer, patiently, while you sleep. So let this part of the story close, in the deep, quiet cold, at the edge of the coldest place there is, where even there, as we are about to discover, the world keeps a small trembling alive. Let your body settle toward its own gentle bottom of quiet. You do not have to reach any perfect stillness. Nothing in the universe does, and that is exactly the comfort. Just let the trembling of the day grow soft and slow, softer and slower, coming to rest as near to peace as living warm things ever come, which is near enough. Rest now. The doorway will wait. Chapter 8. The doorway into the quantum did not open in the deep cold, as it happens. It opened in the glow of something hot, and it opened almost by accident in the hands of a man who did not want to walk through it. Start with something you have seen 1,000 times. Heat a piece of metal, and it begins to glow. First, it stays dark but grows too hot to touch. Then, as it gets hotter, it turns a dull red, then a brighter cherry red, then orange, then a fierce yellow-white, like the filament of an old bulb or iron in a forge. The color of the glow tells you the temperature. The hotter the thing, the more the color shifts from red toward white and blue. This is warmth turning into light, and it is so common that we rarely stop to wonder at it. But near the end of the 19th century, that glow became the biggest unsolved problem in physics. Physicists wanted to explain the exact recipe of that glow. For a warm object at a given temperature, how much light of each color does it give off? How much deep red, how much yellow, how much of the invisible colors beyond the violet? They had good measurements, careful curves, showing exactly how the glow was shared out among the colors, rising to a peak at one color and falling away on either side. All they needed was a theory to explain the shape of that curve. It seemed like a tidy final chore for a nearly finished science. It went badly. When the best classical physics of the day, the physics of trembling motion we have been celebrating all night, was turned on the problem, it gave an answer that was not just a little wrong. It was wildly, catastrophically wrong. The theory predicted that a warm object should pour out more and more light as you looked toward the bluer, higher colors, and beyond them, without limit, more and more energy at ever shorter wavelengths, rising forever. Taken at its word, it said every warm thing, your own body included, should be blasting out an infinite flood of light in the invisible colors past violet, which is plainly absurd. You are not doing that. Nothing is. This spectacular failure earned a dramatic name. People came to call it the ultraviolet catastrophe. Ultraviolet being the invisible color just past the violet, where the nonsense ran off to infinity. So there was a curve, measured and real, showing exactly how a warm thing glows, and the finest theory in the world could not reproduce it, and instead predicted an impossibility. This is the kind of small, stubborn discrepancy that turns out not to be small at all. The man who cracked it was the German physicist Max Planck, a careful, conservative thinker, deeply devoted to the classical physics that was failing him. In the year 1900, working at the problem, he found a mathematical trick that gave exactly the right curve, matching the measurements perfectly across every color. But the trick came with a price he found almost unbearable to pay. To make the numbers work, he had to assume that the trembling sources of the light could not give off their energy in just any amount. They could only release it in discrete little chunks, whole packets of a definite size, never a smooth, continuous stream. Energy, at this scale, came in grains. Sit with how strange that is against everything we had said. All night we have pictured warmth as smooth motion, trembling. That could be any size at all. Energy you could add or remove in whatever amount you pleased, like water poured by the drop. Planck was forced to say no. Down at the level of the glowing, energy comes in fixed smallest amounts, little indivisible parcels. You can have 1 parcel, or 2, or 100, but never 1.5. The size of the smallest parcel was set by a new number of nature, a fundamental constant that now carries Planck's name, almost inconceivably tiny, which is exactly why we never notice the graininess in ordinary life. The steps are so small that the staircase of energy looks like a smooth ramp to our eyes and our hands. And once you assume that, the ultraviolet catastrophe simply dissolves. The reason a warm thing does not pour out infinite blue and ultraviolet light is that light of those high colors comes only in large parcels, and there is rarely enough energy in the gentle trembling of a warm object to afford even 1 such expensive parcel. The high colors are priced out. The glow rises to a peak and then falls away, exactly as the measurements had always shown, because energy comes in packets and the dear ones are seldom paid for. Planck himself was uneasy about what he had done for years. He hoped it was only a mathematical convenience, a bookkeeping trick that would later be explained away and returned to the smooth classical world. It was not. It was the first crack of daylight through the doorway, the first hint that the world, at its smallest, is grainy rather than smooth, made of countable pieces rather than endless continuity. The word for one of those smallest packets is a quantum, and from that single reluctant word grew the whole of quantum physics, the deepest revolution in our understanding of what things are. And notice where it came from. Not from the stars, not from grand cosmic mysteries, but from the plain warm glow of a heated object, from the question of what heat looks like when it shines. The quantum was born from heat. You do not need to carry the equations or the constant or the curve. Carry only the one soft, astonishing idea. Warmth, when you follow it right down to the bottom, does not come in a smooth flood. It comes in grains, in smallest possible pieces, too fine ever to feel, but really there. The world is quietly built of countable parcels, all the way down. Let that settle into the dark with you. The glow of every warm thing, from a candle to a star to your own gently radiating body, is made of these tiny packets, uncountably many, arriving grain by grain. There is nothing to do with the thought but rest inside it. Let it warm you the way the idea of a fire warms you from across a room. And let yourself drift now, softly, carried on the smallest of parcels, toward sleep. Chapter 9. Those tiny packets of light have a name of their own now, and you have surely heard it. We call them photons. Each photon is a single grain of light, the smallest possible piece of a glow. And once you know that warmth can leave a thing as light made of these grains, a whole side of heat opens up that we have not yet touched, because there are, in truth, more ways than one for warmth to travel. All night we have mostly watched heat spread by contact, by trembling atoms jostling their neighbors, handing the motion along, particle to particle. That is warmth moving through touch, and it needs stuff to move through. But you know, from your own life, that heat can also cross empty space where there is nothing to touch at all. The warmth of the sun reaches you across the vast emptiness between here and that star, where there is no air, no substance, nothing to pass the trembling along. It comes as light, it comes as photons, streaming across the void and soaking into your skin, where they set your atoms trembling, and you feel it as warmth on your face. This is the third way, alongside the trembling passed by touch, and the warmth carried by moving air and water. It is warmth traveling as light, and every warm thing does it, not only the sun. A few careful minds worked out its laws before anyone understood the photons underneath. The Austrian physicist Joseph Stefan found, from measurements, how sharply a thing's glow grows as it heats. Ludwig Boltzmann, whom we have met twice already, gave that law a firm theoretical footing, so that together their names are attached to the rule that a hotter object radiates far, far more strongly than a cooler one. The German physicist Wilhelm Wien found the companion rule, the one about color, showing how the peak of the glow shifts toward the bluer end as a thing gets hotter, the very shift you see when metal moves from red to yellow to white in a forge. Now here is the quiet, lovely part, the part that lets you feel this in your own body as you lie there. Everything that has any warmth at all glows. Not only forges and stars and glowing coals, but everything, all the time, including you. Your own body, warm under the blanket, it's softly shining. Not in the colors your eyes can see, but in the longer, gentler waves just past red, the ones we call infrared. You are at this very moment giving off a steady glow of warmth into the room, radiating photons from every inch of your skin. The room, being cooler, glows less brightly back at you, and the difference is part of why a cold room feels cold. You are a soft, warm lamp, shining in colors too deep and gentle for the eye, and you have been shining your whole life without knowing it. There are cameras built to see that glow, and in their pictures, every living body burns like a warm candle against the cooler dark, hands and faces bright, the world sorted into warm and cool by its own light. This is no trick or illusion. It is simply heat doing what heat does when it is warm enough, which is to shine. Every warm thing is a source of light. The warmth of your body right now is quietly leaving you as photons, grain by grain, into the quiet air, and this same idea reaches all the way out to the largest thing there is. The whole universe, long ago, was staggeringly hot, packed close and glowing fiercely everywhere at once. As it expanded and cooled over ages beyond imagining, that glow cooled too, stretched out and gentled, its colors sliding down and down toward the longer, cooler waves, but it never vanished. It is still here. Everywhere you point a sensitive enough instrument, in every direction of the sky, there is a faint, even hum of warmth left over from the young universe, cooled now to just a few degrees above that absolute bottom we spoke of. We call it the cosmic microwave background, and it is, quite literally, the oldest light there is, the leftover warmth of the beginning, still arriving, still faintly glowing all around us. Heat from the dawn of everything, cooled to a whisper, filling all of space. Tonight, gently, forever, so warmth is not only the trembling of atoms in touch. It is also light, made of countable grains, crossing even the emptiest space, connecting a candle to your eye and the sun to your skin, and the first moments of the universe to a quiet instrument on a cool night. Heat travels as light, and light comes in quanta, in photons, in smallest pieces, just as Planck was forced to see. There is something tender in knowing that you are shining, that your warmth does not simply sit inside you, but reaches out, softly, into the room, mingling with the fainter glow of the walls, and the far fainter glow of the sky, and the ancient whisper of the universe itself. You are part of the glowing world, not separate from it. The same kind of thing that makes a star shine is happening gently, quietly along the warm surface of your resting hand. You do not have to do anything with this. Only let it be true, which it is. Let yourself shine into the dark room without effort, the way you always have, giving off your quiet warmth, grain by grain, part of the great soft glow of all warm things. Let that image hold you. And as your body cools by the smallest degree toward the room, as some of your gentle light leaves you and joins the rest, let go a little further, and let the shining carry you easily down into sleep. Chapter 10. If the warmth that shines out of a thing comes in grains, you might wonder about the warmth that stays inside it, the trembling locked into a solid, the shivering of atoms held in place. Does that come in grains too? It turns out that it does. And this is where the little discrepancy in the deep cold, the one that troubled us a few steps back, finally gets its answer. Remember the puzzle. The classical picture said that, as you cool a solid toward absolute zero, its trembling should fade smoothly, and the amount of warmth it takes to raise its temperature by a degree should stay roughly steady all the way down. But careful measurements showed something else. In the deep cold, solids became strangely reluctant to change temperature. It took less and less warmth to shift them, far less than the old picture allowed. The capacity of matter to hold heat seemed to drain away as things got very cold, sliding toward nothing. Near the bottom, the trembling was not behaving like ordinary, smooth, everyday motion. The person who first cracked this was Albert Einstein, in the years just after Planck's reluctant discovery. Einstein took Planck's strange new idea that energy comes in packets, and he applied it not to light, leaving a hot body, but to the trembling of the atoms inside a solid. Suppose, he said, that each atom's shivering in place cannot be just any size. Suppose its trembling energy, too, comes only in fixed packets, smallest steps. The same graininess Planck had found in the glow. Then, something clarifying happens in the cold. Follow it gently. When a solid is warm, there is plenty of energy around, and each atom can easily afford many packets of trembling, so it shivers freely, and the graininess does not show. But as you cool the solid, energy grows scarce, and here is the key. If the smallest possible packet of trembling costs more energy than is going around in the deep cold, then an atom simply cannot afford to tremble at all in the ordinary way. It cannot take a half step or a tenth of a step because there are no half packets. So it falls quiet, unable to buy even the cheapest bit of motion. With fewer and fewer atoms able to afford to tremble, the solid holds less and less warmth, and its capacity to store heat slides toward zero, exactly as the measurements had shown. The mystery of the cold, dissolved the moment trembling, was allowed to come only in grains. Einstein's first version was a little too simple, and here a second name enters: the Dutch physicist Peter Debye, who refined the picture into something that matched the measurements beautifully. Einstein had imagined each atom trembling more or less on its own. Debye saw that in a real solid, the atoms are all linked, so their tremblings are not separate little shivers, but shared waves, ripples of motion running through the whole connected lattice, the way a shiver can run down a bridge or a plucked string hums along its length. Warmth in a solid in this fuller picture is a crowd of these tiny waves of trembling running every which way through the material, overlapping, filling it with motion, and those waves, like the light, come in grains. A single smallest packet of this trembling, one quantum of the shared shiver running through a solid, has earned its own name. We call it a phonon. The word is a cousin of words, like telephone and symphony, all of them rooted in the old word for sound, and that is no accident, because these waves of trembling are, quite literally, the same kind of thing as sound moving through a material, only at the smallest possible scale. A phonon is a grain of sound, a smallest packet of the trembling that carries warmth and tone alike through solid matter. So here is a picture worth holding softly. The warmth inside a solid thing, the frame of your bed, the floor, a stone, a spoon, is not just a vague jiggle. It is a swarm of phonons, countless tiny packets of shared trembling, humming through the material in every direction, carrying the heat from the warm side toward the cool side, grain by grain. When one end of a metal spoon warms in hot soup and the warmth creeps up towards your fingers, what travels up the metal is a flood of phonons, packets of trembling handed along through the linked atoms. Heat conducting through a solid is a gas of these tiny quanta flowing. Notice the pattern that has quietly assembled itself over the last few steps, because it is the deep answer we came all this way for. Warmth that shines across space comes in grains, the photons. Warmth that trembles through solids comes in grains, the phonons. Everywhere we look, when we look closely enough, the smooth flood of heat resolves into countable smallest pieces. The world that felt continuous, warmth you could pour and divide without end, is underneath a world of parcels, of quanta, of little indivisible steps. Heat is motion, we said long ago, and now we can say it more truly. Heat is quantized motion. Motion that comes in grains. There is a strange comfort in that if you let there be. The warmth around you and within you is not an endless, smooth ocean. but something made of small, definite, countable things, each one gentle, each one tiny, adding up to the soft heat that holds you. The trembling in the walls, the humming phonons in the floor, the quiet infrared shine of your own skin, all of it built from the same smallest pieces, the same patient graininess underlying everything warm. You do not need to count them. Nothing asks you to. Let the phonons hum through the solid dark around you, a numberless soft chorus running through the frame of your bed and the boards of the floor, carrying warmth so gently you will never feel a single grain of it. Let that quiet music be a lullaby made of the smallest possible sounds, humming under everything, asking nothing, and let it carry you, packet by packet, down into rest. Chapter 11. Now, we can go back and finish something we left unfinished, down in the deep cold, at the very bottom of things. We stood at the edge of absolute zero, and I told you the classical story made a clear promise there. At the coldest possible cold, it said, all trembling stops, every atom perfectly still, motion gone entirely, and I told you, quietly, that this turns out not to be true. Tonight we can see why. The reason is one of the strangest and most beautiful facts the quantum world has given us. And it was first written down clearly by the German physicist Werner Heisenberg. He found, working through the new physics of the smallest things, that nature refuses to let any tiny particle have both a perfectly definite position and a perfectly definite motion at the same time. The more exactly a particle is pinned to one spot, the more uncertain and unsettled its motion must become, and the more exactly its motion is fixed, the more its position blurs and spreads. You cannot have both sharp at once. This is not a limit of our instruments or our cleverness. It is woven into what a particle is. We call it the uncertainty principle, and it is one of the deepest truths we know. Now watch what that does to our dream of perfect stillness. To bring an atom completely to rest would mean giving it exactly zero motion pinned down perfectly to nothing at all. But an atom held in a solid is also held to a place, more or less fixed in its spot in the lattice. Nature will not allow both a definite place and a perfectly definite zero motion, because that would be having position and motion both perfectly sharp at once, the very thing forbidden. So the atom cannot come fully to rest. Even when you have taken away every last scrap of ordinary heat, even at the absolute bottom, where the classical story insists all motion should be gone, a residue of trembling remains, a smallest irreducible jiggle that cannot be removed by any cooling whatsoever. It is not warmth, it is deeper than warmth. It is the trembling that the very nature of things requires. We call it 0-point motion, or 0-point energy, because it is the motion that remains at the 0 point of temperature, at the coldest cold. It is the floor beneath the floor. You can cool a thing until every bit of ordinary heat is gone, until it is as cold as the laws of the universe permit. And still, down in the atoms, there is this faint, permanent, restless shimmer, humming on, unremovable, forever. Nothing in the universe is ever perfectly still. Nothing ever has been. Nothing ever can be let that sit gently with you, because it turns the fear of a dead, frozen stillness completely inside out. There is no absolute frozen stop waiting at the bottom of things. No perfect deathly stillness anywhere in all creation. Even the coldest atom in the coldest corner of space keeps its small trembling alive. The universe, at its very quietest, is still softly moving. Stillness, complete and total, is simply not a thing that exists. Existence itself trembles. This is not some tiny academic footnote either. That permanent trembling has real and measurable effects. It keeps certain substances, like helium cooled to extraordinary depths, from ever freezing solid under their own gentle weight, because the 0-point jiggle keeps shaking them liquid when the classical story says they should have long since frozen. It leaves fingerprints in careful measurements of very cold matter. It is even woven into the empty vacuum itself, which is never truly empty, but always faintly humming with this deepest kind of motion. The restlessness goes all the way down and all the way through. There is no bottom where it stops. Think of what that means for the question we set out with. All those steps ago, we asked what heat is made of, and we have followed it down through fluid and motion and grains. And now, at the very bottom, we find that motion never entirely ends. Warmth is trembling that comes in grains, and beneath even the last removable grain, there lies a trembling that can never be taken away at all, built into the fabric of what it is to be a thing that exists in a place. The world is restless to its foundations, not violently, not harshly, but gently, permanently, at the smallest possible scale, everywhere, always. There is a deep peace available in that, I think, if you reach for it. As you lie there in the dark, you have spent your whole life, perhaps, chasing after stillness, after a perfect quiet where everything stops. And here is the universe telling you, kindly, that such a stillness does not exist and never did, not in the coldest star, not in the emptiest space, not at the absolute bottom of all cold. The gentlest possible motion is the truest rest there is. You do not have to become perfectly still to be at peace. Nothing is. The whole quiet universe is trembling softly beside you, and it has never once found that a reason not to rest. So let go of the last small effort to hold yourself completely still. You were never meant to. Let your breath keep moving, your heart keep its quiet drumming, the faint, warm trembling of every atom in you humming softly on, exactly as it should, exactly as the coldest star does, exactly as the empty dark between the galaxies does. That gentle, endless, unremovable trembling is not the enemy of sleep. It is what sleep is made of. Let it hum on beneath you, the floor beneath the floor, holding you up, and let yourself sink into it, softly, and rest. Chapter 12. We have found the floor beneath the floor, the trembling that never stops. Now let us come back up just a little and ask a gentler question. When many tiny particles share a bit of warmth among themselves, how do they divide it? Who gets to move, and how much, and why? Because the quantum world changes even the sharing of heat in a way that leads us to the coldest, stillest matter ever made by human hands. In the classical picture, sharing warmth was like sharing coins among a crowd where everyone is a distinct individual. You could tell each person apart, and you counted the ways of handing out the coins accordingly. But the quantum world revealed something that has no everyday parallel at all. Identical particles are not merely similar. They are truly, perfectly indistinguishable in a way that changes the very counting. 2 photons of the same light, 2 atoms of the same kind in the same state, are not 2 individuals who happen to match. There is genuinely no fact about which one is which. And when you cannot even in principle tell them apart, the arithmetic of how they share energy comes out differently. This was first understood for light. A young Indian physicist named Satyendra Nath Bose, working far from the centers of European science, found a new and correct way to count the ways that identical grains of light could share out among the available states of energy. He sent his work to Albert Einstein, who saw at once how important it was, translated it, and extended it from grains of light to atoms of matter. Out of this came a new statistics, a new law for how whole crowds of identical quantum particles arrange themselves, quite unlike the classical counting of distinct individuals. For a certain broad family of particles, the ones that light and many atoms belong to, this Bose and Einstein counting is the true one, and it predicted something astonishing, something Einstein worked out and then almost did not quite believe. For that family of particles, if you cool them far enough, so cold that there is almost no warmth left to keep them jostling in their separate states of motion, they do something no classical crowd would ever do. They collapse together into the single lowest state, all of them at once, settling into exactly the same gentlest possible motion. Not merely side by side, but genuinely merged, doing the very same thing, indistinguishable and unified, like a great many voices falling into a single perfect note, a whole crowd of atoms behaving as one. For 70 years, this remained a prediction on paper, because reaching the required cold was beyond anyone. To make it happen, you would have to cool a cloud of atoms to within a hair of absolute zero, colder than the coldest depths of space, colder than anything nature makes on its own anywhere we know of. It took the patient invention of extraordinary new ways to chill matter, using beams of laser light to slow atoms down, and clever magnetic traps to hold the coldest ones while the warmer ones were let escape, carrying the heat away with them the way steam carries heat off a cooling cup. In 1995, it was finally done. The American physicists Eric Cornell and Carl Wieman, working together, cooled a small cloud of atoms to within billionths of a degree of the absolute bottom, and watched them fall together into that single shared state, exactly as the theory had promised. Not long after, the physicist Wolfgang Ketterle achieved it as well with larger clouds and refined it further. This new form of matter, a crowd of atoms merged into one quantum whole, is called a Bose-Einstein condensate, after the 2 men who first imagined it. It is, in a real sense, some of the coldest and stillest stuff that has ever existed in the universe, made deliberately, gently, in a handful of quiet laboratories on Earth. Think about what that means for our long question about heat. All night, we have said that warmth is motion, trembling, the restless jostling of tiny things. A Bose-Einstein condensate is what you get when you take almost all of that away, when you drain the warmth down to the very edge of the permanent 0 point trembling we found beneath the floor. The atoms stop jostling as separate things and settle into one calm, shared, unified motion, as still as matter is allowed to be. It is as close to the absence of heat as anything ever comes, a hush at the bottom of the world made on purpose. And even there, remember, the 0 point trembling hums on. Even the coldest matter ever made is not perfectly still. Nothing ever is. There is something quietly moving in the picture of it, a cloud of countless separate atoms, each one its own restless thing, cooled so gently and so far that they let go of their separateness entirely and become one, moving as a single soft whole at the very threshold of stillness. It is a kind of settling, a kind of coming to rest together that only the deepest cold allows. You are far warmer than that, of course, warm and alive and gently trembling as you should be. But you can borrow the shape of it as you lie there, the letting go of separateness, the settling together into one quiet motion, the coming as near to rest as a warm thing ever comes. You do not need billionths of a degree for that. You only need to loosen and let the day's separate busy motions fall together into one slow rhythm, the rhythm of your own quiet breathing in the dark. Let the countless small restlessnesses of your body settle toward a single gentle calm, and let that calm, warm and unified and softly humming, carry you down, all the way down, into sleep. Chapter 13. There is one more strange and lovely thread to gather before we close the night, and it ties heat to something you would never expect. It ties heat to knowledge, to information, to the difference between remembering and forgetting. It begins with a puzzle that James Clerk Maxwell, whom we met building the picture of heat as motion, dreamed up long ago as a kind of playful challenge to himself. He imagined a tiny, clever being, later called Maxwell's demon, guarding a small door between two halves of a room full of moving air. Remember that in any warm gas, some molecules move faster and some slower. The demon watches, and every time a fast molecule comes toward the door from the left, it opens the door and lets it through to the right. And every time a slow one comes from the right, it lets it through to the left. Slowly, molecule by molecule, without any apparent effort, the fast ones gather on one side and the slow ones on the other. One side grows warm, the other grows cool, all by itself. You should feel a small alarm at that, because it seems to break the deepest rule we found. Warmth was supposed to spread out and even off, entropy always rising, hot and cold, never sorting themselves apart on their own. Yet here is the demon, quietly separating hot from cold, seeming to run the whole one-way street of heat backward, using nothing but knowledge, nothing but seeing which molecule is which. For a long time, this imagined little creature genuinely troubled physics. How could simply knowing things let you cheat the flow of heat? The answer took most of a century to work out fully, and it is one of the most surprising results in all of science. The physicist Leo Szilard, thinking hard about the demon, saw that the act of measuring which molecule is fast or slow, the act of getting the information, must itself have a cost that has to be paid back into the ledger of entropy. And later, the physicist Rolf Landauer, working at a company, that built computers and cared about the physics of information found the sharpest form of the answer. He showed that it is not really the knowing that costs. It is the forgetting. Whenever information is erased, whenever a memory is wiped clean and a record is thrown away, a definite smallest amount of heat must be released into the surroundings. Erasing a single bit of memory warms the world by a tiny, unavoidable amount. The demon, to keep working, must eventually forget what it has seen, clear its little mind to watch the next molecule, and in that forgetting it pays back every bit of order it seemed to steal. The books always balance. Heat is not cheated after all. Sit for a moment with how deep and unexpected that is. Information and heat, which seem to live in completely different worlds, the world of minds and records on one side, and the world of warmth and motion on the other, turn out to be the same kind of thing at the bottom. To erase a memory is to release warmth. Every computer running tonight, every phone, every machine that thinks, warms the air around it in part for exactly this reason, because it is constantly forgetting, constantly clearing away old information to make room for new, and each forgetting carries its small, unavoidable heat. The warmth rising off a working machine is, in part, the physical price of forgetting. This is called Landauer's principle, and it draws a line straight from the abstract idea of information to the plain warmth you can feel with your hand. And there is a final grain to mention, fitting for a night spent finding that everything comes in smallest pieces. We have seen that warmth stored and carried comes in grains, the photons and the phonons. It turns out that even the flow of heat, the sheer rate at which warmth can pass through the narrowest possible channel, has a smallest step of its own. If you make a bridge for heat thin enough, down to a single tiny thread along which the trembling must pass, the warmth cannot trickle across at just any rate. There is a smallest possible unit of heat flow, a quantum of thermal conductance, a finest rate at which a single channel will carry warmth from the hot side to the cold. And this is not only theory. In delicate experiments, in the deep cold, physicists have actually measured this smallest flow, watched heat cross a single channel at exactly the quantized rate the theory predicted. Even the flowing of warmth at the very bottom comes in grains, so the pattern we have been following holds all the way to the end, and further than we might have guessed. Heat stored comes in grains. Heat shining comes in grains. Heat trembling through solids comes in grains. Heat flowing through the narrowest channel comes in grains. And heat is bound up in the deepest way with information, with memory and forgetting, with the very difference between order and its spreading. The plain warmth of your mug, followed all the way down, turns out to touch nearly everything. The motion of atoms, the shining of stars, the passage of time, and the physics of thought itself. That is a great deal for one small sensation to contain, and you do not have to hold any of it firmly tonight. Let it be enough to know that the warmth in your hands is quietly connected to the deepest workings of the world, and that you have followed the thread a remarkably long way, from an imaginary fluid to the smallest possible flow of heat, and that you are allowed now to set the whole thread down, Let your thoughts stop sorting and separating, the way the demon finally must. Let the day's information settle and blur and be gently forgotten, warming the quiet dark by the smallest breath, the way all forgetting does. There is nothing left to sort tonight, nothing left to keep. Let it all even out, warm and soft around you, and let yourself drift, unsorted and unhurried, towards sleep. Chapter 14. So here we are, at the end of the long night, ready at last to answer the question we cupped in our hands at the very beginning. What is heat made of? Let us gather the whole journey into one quiet place and say, as honestly and as gently as we can, what we have found. We began with a warm mug and a simple feeling, warmth crossing into your hand, and a plain question about what was moving. And the first thing we learned is what heat is not. It is not a fluid. For a long time, the most careful people alive believed it was. An invisible, weightless, something called caloric that poured from hot things into cold ones. And they had good reasons, and they were wrong. Benjamin Thompson watched heat pour endlessly from a boring drill and saw that no fluid could be so bottomless. James Prescott Joule measured, with a falling weight and a bucket of water, the exact price at which motion becomes warmth, and showed that heat is a form of energy, never made from nothing, never destroyed, only passed from one form to the next in an unbroken accounting. Then we found what heat is. Heat is motion, the restless trembling of the tiny pieces of matter, the atoms and molecules, flying and jostling in a gas, shivering in place in a solid, never still. Temperature is just how briskly they tremble, and the warmth you feel crossing from the mug is that trembling handed along, particle to particle, from their pieces into yours. And we found why warmth only ever spreads and never gathers, why it flows from hot to cold and gives time its single direction. Because a shared, evened out motion is so overwhelmingly more likely than a gathered one, when the numbers are as vast as they are. And then we stepped through the doorway into the quantum, and the answer deepened into something stranger and finer. The motion that heat is made of does not come in a smooth, endless flood. It comes in grains, in smallest possible pieces. Max Planck found the first grain in the glow of a hot object, forced against his own wishes to say that energy comes in packets. And from that reluctant grain grew the whole picture we have wandered through tonight. Warmth that shines across empty space comes in photons, grains of light, the same grains that carry the sun to your skin, and the oldest glow of the young universe to a quiet instrument on a cold night. Warmth that trembles through a solid comes in phonons, grains of shared shivering, humming through the frame of your bed and the boards of the floor. Even the flow of heat through the narrowest channel comes in smallest steps. Heat is quantized motion, motion cut into grains too fine to feel, and beneath even the last removable grain, we found the deepest thing of all. Motion never entirely stops. The uncertainty at the heart of the quantum world forbids perfect stillness, so that even at the coldest cold, even in matter, chilled to within billionths of a degree of the absolute bottom, a faint permanent trembling hums on, unremovable, forever. There is no dead frozen stillness anywhere in all creation. The universe, at its very quietest, is still softly moving. Existence itself trembles. So what is heat made of? It is the trembling of everything there is. Not a substance of its own, not a fluid you could catch in a jar, but the ceaseless, quantized, restless motion of the smallest pieces of the world, and the light that motion shines out, and the way that motion spreads and shares and gives time its direction. When you feel warmth, you are feeling the trembling of the world touch the trembling of your body. That is all it ever was, and it is everywhere, in the walls, in the air, in the ancient glow that fills all of space, in your own quietly shining skin. Notice, too, what we could not say, because honesty is part of the gift. There are still open edges to this. Physicists are still working out exactly how heat and information and gravity fit together at the very deepest level, still measuring the smallest flows, still probing the strange cold. The picture is not finished, but the heart of it is as solid as anything we know, tested 10,000 ways, true in every laboratory. Heat is the quantized trembling of matter and light. On that, the whole long story agrees. And there is such comfort in it. On a night like this, you spent your life perhaps imagining that rest meant becoming perfectly still, perfectly quiet, perfectly stopped. And the whole universe has spent this night telling you gently that it does not. Nothing is ever perfectly still. The coldest star trembles. The emptiest space trembles. The atoms in your resting hand tremble, and will go on trembling softly all night. And that faint, endless motion is not the opposite of rest. It is what rest is made of. You do not have to stop. You never could. You only have to let the trembling grow, soft and slow, and even, the way warmth always does when it is left in peace. So let it. Let the warmth of your body spread gently into the sheets and the quiet air, evening out, sharing itself with the room, exactly as the whole universe is slowly, patiently doing everywhere, forever. Let the photons leave your skin in their soft invisible glow. Let the phonons hum in the floor. Let the day's motions fall together into one slow rhythm, the rhythm of your breathing, the gentlest trembling there is. You followed the thread all the way to the bottom of the world and found only warmth and motion and the smallest kind quiet trembling, holding everything, holding you. There is nothing left to do now, nothing to solve, nothing to catch, nothing to hold still. The warmth will keep crossing gently into you and out of you all night, grain by grain, the way it has since before you were born. The universe will keep its soft trembling watch, and you can let go of the thread completely now, and rest, warm and held, exactly where the trembling world is quietly keeping you. Sleep well. Good night.